All right, this is a screencast on the families, the organic families that feature the carbonyl functional group. The carbonyl functional group is the C double bond O, and the families that we're talking about are the aldehydes, where the carbonyl group is terminal. Okay, so that means the carbonyl group is at the end. Or the ketones, where the carbonyl functional group is somewhere in the middle. Okay, so we have the aldehydes and the ketones. All right, so another way of looking at it is for aldehydes, they will always have that terminal carbonyl group. So if you identify where the carbonyl group is in an aldehyde, you're going to see it's at the end. Okay, it's going to have just a hydrogen connected to that carbon, and then the rest of the carbon chain goes that away, right? Whereas for a ketone, you're going to see that the carbonyl group is always somewhere in the middle of the molecule. Okay, so you'll have a carbon chain going that way and a carbon chain going that way. In other words, it's non-terminal. And what this also means is that the smallest possible ketone you can have is going to be a propanone. Okay, it's going to be at least a 3-carbon ketone. That's the smallest. So if we work on naming aldehydes a little bit based on the IUPAC naming system, so they get the suffix al. Okay, so they get like al, or you might say it's actually anal, all right, on the end of it. This is as opposed to what you would put on an alkane, like ane. Okay, so for example, this first one, if we look at the series here, there's only 1 carbon, so this is going to be, for the 1 carbon prefix meth, we'll call this methanal. Okay, for the 2 carbon, we would call this ethanal, and for the 3 carbon, we would call this propanal. Okay, you don't have to identify the position of the carbonyl group, because we know, because it's an aldehyde, that the carbonyl group is always terminal. It's always going to be on the very last carbon. Okay, what you also might be able to predict from this homologous series of aldehydes is that as you progress downwards and the molecules get larger, they'll have a predictable change in their physical properties, and that we will see a melting point or boiling point increase, right? We have an increasing number of electrons, and this is a trend for all organic compounds. As they increase in size down a homologous series, the melting points and boiling points increase because you have an increased dispersion force from the greater number of electrons. All right, a little bit of aldehyde naming practice. So once again, when we're trying to name any organic compound based on the IUPAC naming system, the first thing we want to do is recognize what's the longest run of carbons. Okay, and so for the first one here, the longest run is clearly 4. You might think of it as that set of 4, or you might think of it as this set of 4. Doesn't really matter. Longest run is 4, and so we know that the prefix being used here is going to be but. Okay, and we know this is going to be butanal because, of course, we've got the terminal carbonyl group making it an aldehyde. Okay, so a lot of that's visual recognition stuff, right? Now, in terms of the numbering here is important because we do have an alkyl substituent. We have a little methyl group that's stuck on there. The question is this carbon number 2 that it's stuck on, or is it carbon number 3? And the answer is you number the carbons in the parent chain to give the functional group priority. So we give, in this case, the carbonyl group priority. So we're going to number this carbon 1, 2, 3, 4 like that. So this is going to be 3-methyl butanal. That's the proper name for this. And I almost left myself space to write it. 3-methyl butanal. Okay, if we look over to the one here on the right, What's the longest run of carbons in this chain? Well, it's going to be 1, 2, 3, 4, 5. Okay? Or you can think of it like this, 1, 2, 3, 4, 5. Again, it doesn't really make a difference. You can also, of course, tell that this is an aldehyde because the title of this is Aldehydes, and also because it has a terminal carbonyl. All right? So again, we're going to number this chain. Well, anyways, we know it's a pent. We know it's pentanal because there's 5. Let's get that down there. And we're going to number this chain 1, 2, 3, 4, 5. Number the carbons in the parent chain to give priority to the carbon that has the carbonyl group on it, right? And we know the substituent in this case is a 2-carbon substituent. It is an ethane residue called an ethyl group. So we are going to identify the position of ethyl group on carbon 3. This is 3-ethyl pentanal. Should all be one word. All right, let's flip to some ketones. Okay, now, again, realize the difference. We've got a carbonyl group for these that is somewhere in the middle. Okay, so we also have some alkyl substituents to deal with and everything else. But we use the suffix -one for ketones. So we drop the ane like we would for an alkane, and we use -one. So if we look at the first one here, top left, this is the smallest possible ketone. This is going to be propanone. And you can just call it propanone. That's okay. Because there's really only one position that the carbonyl could be in for this. Now, alternatively, you could call it propan-2-one, and you would be correct. It's the same one, right? And hopefully you realize that. Down below that, we have 1, 2, 3, 4, 5 carbons in this structure. So this is going to be a pentanone. We have to name the position of the carbonyl group here. So it's going to be on carbon 2. So it's going to be pentan-2-one. Okay, and there's no substituent, so that's it, pentan-2-one. For this last one down here on the right, we got to do a little bit of thinking. So what's the longest run of carbons? Well, you can identify this 6-carbon run as the longest, or you could identify this 6-carbon run as the longest, or you could identify this 6-carbon run as the longest. Yikes. So what do? Well, the red one and the yellow one turn out to be the exact same thing. If you don't believe me on that, pause it and have a look, and you'll see that they're one and the same, the yellow and the red. The green one is a little bit different, and what the green one would do is it would generate a very large alkyl group. It would generate this like 3-carbon isopropyl alkyl group on the end, and what we try to do is actually number. This is kind of a really specialist thing that hopefully you never have to sort out on your own, but we try to number and identify the parent chain to try and reduce the size of the alkyl groups as a priority. So anyways, we're not going to do that. We're going to use the yellow or the red as the parent chain. Okay, and then we're going to number the carbons again like we always do to give the functional group, the carbonyl group, the highest priority. So we're going to number it 1, 2, 3 from left to right, 4, 5, 6. The alkyl groups are thus a 4-ethyl, right, and a 5-methyl. All right. So check the alphabetical order. E comes before M, so we will also express the ethyl before the methyl. So we are going to call this 4-ethyl. 5-methyl, and then it was 6, so it's hexane. And then what's the position of the carbonyl? It's on carbon 3, hexane 3-one. Phew. All right, a little bit about the physical properties of aldehydes and ketones. So first of all, aldehydes, are they water soluble? And the answer to this is generally yes, they are. What they can do is they can hydrogen bond with water. Okay, so because water has those highly partially positive hydrogens, they can make a strong association with the double bonded oxygen there, and they can hydrogen bond with water. Same with ketones. They're also water soluble, and they can hydrogen bond with water. Okay? With water. They also stick quite strongly to each other, okay? But they can't, quite curiously, they cannot hydrogen bond to one another, because to do that, you have to have like an O and an H connected, or an N and an H connected. So they cannot H bond with one another, but still they form strong dipole interactions with each other. Both of them do in this group. So we could say that they have dipole, okay, and same dipole. And you'd have to analyze on a case-by-case basis how strong it was for the certain molecule. But generally speaking, aldehydes and ketones have higher melting points and higher boiling points than their similar sized hydrocarbons. So in other words, like you would expect this one at the top, ethanal, to have a higher melting point and boiling point than the comparable ethane. You would also expect this ketone here, propanone, to have a higher melting point and boiling point than its adjacent hydrocarbon, propane, okay? Because propane and ethane, they can only associate with neighboring molecules via dispersion force or London force, whereas these guys, as aforementioned, have dipole-dipole force between adjacent molecules, and so they stick together a little more strongly. Hope you found this helpful.